G'day viewers. In this segment we'll talk about equal cost multipath routing. That's a mouthful, but it's really an extension to the shortest path routes we've seen before. What we would like to do now is to allow the use of multiple routes between a given node and a destination. In everything we've seen so far with the shortest path formulation, we picked a single path from a node to a destination. But what if you want to allow multiple paths? For instance, in this network, to get from A to E, you could see I could take this path here, or there's another path through the topology, which actually turned out to be our shortest path before. I could allow both of these to be used at the same time. That's what we're going to look at. The general name for this procedure is multipath routing, the use of multiple paths. Now, these multiple paths usually exist in the topology already, and the reason for that is you want to provide enough links in your network topology for redundancy. In case one link fails, you want to be able to have a different link to reach a destination. So there probably were multiple paths somehow. We would just like to be able to use them both at the same time during forwarding, and the reason for this is simply to improve performance. Maybe we can fit more traffic through the network if we can use these multiple paths. What we're going to look at now is really a simple extension to our framework so far to incorporate multiple paths. It's fairly straightforward. There are really two questions we need to answer. How do we find these multiple paths as opposed to finding a single path we did before? And when we have them, how do we use them for forwarding? So the first question is about routing, the second question is about forwarding. Given that we have multiple paths, how do we use them at the same time to send traffic? So let's go through these questions, and we'll do it in the context of equal cost multipath routing. This is really one form of multipath routing, which is an extension of our shortest path model. All we do here, the extension really is to keep a set of next hops and routes if there are ties. Previously we just chose one randomly when the costs happened to be the same. There was one that was not a unique minimum cost. So here's our picture of a network again, just to illustrate that. And I've changed a few of the costs here in red. And I've changed it so that, now we're going to have some paths, multiple paths, which have the same minimum cost. So you can see them in this graph. I've sketched them, but we can just compute them to make sure that they're okay. The path A, B, E is one way to get from A to E. That has cost 8, okay? Well, there's also another path, and that is the path A, B, C, E. That has cost 4 plus 2 is 8 again. And there's even another path which goes A, B, C, D, E. That is more hops, but it happens that the cost of these hops is lower, and so when you add it up, guess what you get again? 8. All of these paths are the minimum path, and in our equal cost multipath formulation we'd like to use them all. Now, equal cost multipath, since it generalizes shortest path routing, it actually changes our notion of a source tree and a sink tree. With ECMP, these source and sink trees are actually not trees anymore. They become a slightly more general structure called a DAG, which stands for a directed acyclic graph. Now, in a normal tree, we have a structure like this on the left, and you can see just a classic hierarchical tree there. To get to a particular destination, there's just one next hop. In a DAG, however, you can see I've added some of these cross-links. Every node can have a set of next hops that it can use to reach a destination. So for instance, there are two paths through here from the source to the one destination. So that means from the root I could go either of two different ways and I would still be able to arrive at this same particular node down at the bottom. It's a DAG, it's acyclic, so there are no cycles or loops in this topology. As you follow paths through here, you'll definitely get to a destination without going round and round in loops. So we haven't admitted loops. There's also still a compact representation for routing. Each node now has not a single next hop, but a set of next hops to reach a destination. But we don't need to have nodes store the entire path or anything like that. Let's just see a little bit of an example. Here's our graph again. Now we'd like to find the source tree, or really DAG, for E. The procedure that we go through is simply Dijkstra, but keep all of the ties instead of randomly picking one. And then once we've got this tree, we'll be able to compile it into a forwarding table. I'm not going to show you here, but you'll find that as well as Dijkstra, there's also a straightforward extension for distance vector, where instead of choosing one minimum cost route, you can keep multiple of the minimum cost routes, the set of neighbors if you like. Okay, let's see that source tree for E. Well, let's see, I'm going to start going out with minimum cost. From E we can reach D here. Now at distance 2 we can get to F, we can get to C. Now interestingly, this is where things have been added. I can get to C in two different ways. The direct loop route here and via D. It still costs 2. And we can then go on adding other paths through the network. So for instance, to get to H, well, let me do B first. To get to B, you can get to B here over this loop, but you can also get to B along this path. They both have cost 4. And similarly, we're going to get to A along here, H along here, and F along here. None of this has changed. And this is the shortest path, the source tree, which is really a directed acyclic graph. If I just flip ahead, you'll see, now hopefully they were actually the same as what I drew, that there are 2 new lines here that really got added with the ECMP case. Just tracing over them. We can now compile, so this is just a source tree as before, but a slight generalization of it. You can verify that for yourself. We can now compile this into a forwarding table. It's the same procedure as before, just mapping from a tree down to all we need to do is remember the next hops. But you'll notice here that to get to certain destinations, I have a choice of next hops. One of the biggest ones is to get from E to A. I can go many different ways. We had seen I could go this way. These are the examples I sketched before. I could go this way, or I could go this way. 3 different paths, all of minimum cost 8. That means from E, I could choose any of B, C, or D as the next hop, and you can see that in the table. Now instead of one entry, we have multiple entries. And you can go through the rest of the table, and you can see that I've colored in pink there some of the entries that now differ. They have sets instead of the single next hop. Well, that's it for the routing. What about the forwarding? We like to forward with these equal cost multipaths. One way you could do this is when you have a packet, since you only want to send the packet down to one neighbor, otherwise we'll be making copies of it. You could simply choose at random for every packet which of the next hops to use. That's this option here. That's actually very effective in terms of balancing traffic across all of the different paths. However, it adds jitter. Now what I mean by this is that the different nodes going from a given source to a given destination might experience quite different delays through the network. For instance, maybe if you send packets 1, 2, 3, 4 at a particular node, 1 and 3 and 4 will all take a certain choice, which is a shorter path physically. And in terms of seconds, I mean, the cost is going to be the same. Whereas path 2 might randomly be chosen to take a different next hop, which will be a more circuitous route, which will take longer. So we might send packets 1, 2, 3, 4, but they might be received at the destination 1, 3, 4, because they took the short path, and a long time later, packet 2 will arrive. You can imagine this can get a little complicated for the receiver to work out things. So we would like to avoid these kind of effects. So instead, what we'll try to do is send packets from a given source-destination pair on the same path. This is, imagine if you've got a video conference. It's between it's a set of traffic, or a flow, this is sometimes called, traffic between a particular source-destination pair, often for a particular purpose, is called a flow. We would like to send the traffic from a given flow along the same path through the network. This way the ordering of packets within it should be preserved. We shouldn't get any of this wild jitter. So all we do to handle this is we make the choice not at random per packet, but we map a flow to a single next hop. How do we do this? Well, here's an example. I've shown the paths here, just a segment of the paths that range from F to H. And you can see we have different paths through the network. We might go this way, or we might go this way. This also includes, by the way, the paths from E to H. We can take those different choices, and the paths from F to C, and the paths from E to C as well as E to H. Well, I said one twice there, but you can see that there are 4 different source-destination pairs. I've listed them here as flows, traffic from F to H and F to C, as well as E to H and E to C. Now, for all of these different flows, as they go through E, they could be sent either to C or D. Instead of choosing at random, we'll simply make this set of choices. For the packets that come from F, we'll send them to D, and for the packets that come from E, when they're going to H or C, we'll send them to C as a next hop. In this way we have some consistency for the flows, but if we think about traffic that's heading towards C, we're actually using both of the next hops. We're using D and C. So traffic towards those destinations is utilizing multiple different paths through the network in parallel. And that's how we forward with ECMP. Now you know this slight generalization of the shortest paths we've seen before.